Good morning, everyone. My name is Chee. I'm from Zendesk in Australia. I've worked on the first 3 machine learning products at Zendesk, and that's my dog, Pepper. I'm one of those weird people that like to put dog photos everywhere. So today, I'll be talking about how we build machine learning models initially at Zendesk with our first product by using Hadoop and some of the problems we face with that approach. So with some of the more recent machine learning product that we worked on, we realized that we have to support training much larger number of models concurrently. And as a result, we have to evolve our model building infrastructure to support the higher requirements. And along the way, we've learned some lessons and we made some mistakes. And I'll be talking about some of those as well. So if you're working on a new ML product, or if you work on a similar problem space, hopefully some of these learnings could be helpful for you. As we all know, scaling up systems can be painful. It involves a lot of blood, sweat, and tears. Sometimes might leave some bitter taste in your mouth. If you're training, say, for example, 1 or 2 models, it's easier to sort of debug when things go wrong. But say, for example, if you're training thousands of models in parallel, and let's say, for example, if you have some resource contention or you have some bottlenecks, some of those model building jobs could fail, 1 or 2 of them, or a big bunch of them, right? And therefore, it's important to ensure that your model building infrastructure is resilient and is able to cater for different data profile across your different model building jobs. Before I get into the details of our model building system, I'll just briefly explain what Zendesk is. We are a software company that help our customers maintain their interactions with their end users. So say, for example, if someone raises a support ticket, that goes into our software and we sort of maintain the sort of back and forth between the support agent and the end user. We also provide the ability for our customers to host their FAQs or knowledge-based articles such that they can help their end users self-serve. And the ML journey at Zendesk started, I would say, quite recently compared to a lot of the big companies. We launched our first ML product in 2016. It's called Customer Satisfaction Prediction. And for that, we have to build up to 3,000 models every week, so we refresh that every week. And so this was actually our first ML product, so obviously we were trying to dip our toe in the water. And the way it works is that any support ticket that comes in, we predict whether the customer is happy or not happy. And if the ticket is updated again, we run the prediction again. So it's basically sentiment analysis. And back then, a lot of our infrastructure was still kind of living within our own data center. So we haven't migrated into the cloud yet, which means we run our own Hadoop clusters, our own managed Hadoop clusters in our data center. And within it, it is acting kind of like our data lake. We stored all the support tickets in our Hadoop distributed file system. And then we would have MapReduce job to extract features from those data. And then we would run the model training on those data as well. And the model training are basically just Python code. And at this stage, we were using logistic regression. And at the end of the job, we will write out all the models files stored as a Pico format, a serialized Python format. And every run of the job, we will run up to 400 models for every batch, and we'll repeat that every day. And well, this works for satisfaction prediction and the scale that we need to meet, but very soon we realized that Hadoop wasn't the right tool for this. To achieve the fault tolerance and scalability, Hadoop wants to control how you package, configure, deploy your code. Which means it's not that straightforward if you want to use, say, for example, a different Python libraries, or say, for example, if you want to swap your ML code from Python to R or other languages. And also because like all these jobs are run in batches, and sometimes for an ML product, you want to trigger some ad hoc model build for just one account, one customer. Why? Because say, for example, if someone just joined, just sign up for these new features, this new ML product, you want to make the model available for them as soon as possible, which means you want to just build for this customer without waiting for the next scheduled run to happen. And that's not the kind of use case that Hadoop would support natively. And we knew that we have to improve on our model building infrastructure. But when we get to our second ML product, which is AnswerBot, we didn't really have to do that. Why? Because Answerbot uses deep learning model, which means we have one universal model for all the accounts. We don't have to build model for each account. And because it's deep learning, and we only refresh those models when our data scientists decided to, say, for example, change the neural network architecture, which means we don't rebuild them often, maybe only every couple of months. And the way Answerbot works is when a support ticket comes in, say, for example, if someone asks about shoe size, we find the most relevant knowledge-based articles that can solve that ticket, and we suggest it to the customers. So they can choose to close the ticket themselves if that helps them with their query. And the science or the ML behind it works such that it uses the document embeddings, which means the model actually learns the meaning of phrases. Say, for example, if you have a phrase like this, we are all prisoners of our phones, thus they are called cell phones. And then what the ML model does is that it embeds this phrase into a vector of numbers. So that represents the meaning of that phrase. So if we imagine all these blue dots, like this is the embedding space. If we imagine all these blue dots to be a phrase, say, for example, you have a phrase about men with heels. You have a phrase about they is not necessarily plural, and one about short-haired women. So all these phrases are related to gender identity, so they are close to each other in the embedding space. And phrases that are more different, say, for example, like tenderloin is the best part of SF, that would be on a different corner, and smell of weed. So that's how you encode the different meanings of phrases. And if we imagine all these yellow dots to be knowledge-based articles, and when a ticket comes in for an account, we basically find the closest articles to that ticket, and we suggest it to the customers. So that's how Answerbot works. And then sometime last year, we got to our third machine learning product called Content Queues. We launched it for early access in April, and for this, we have to train up to 50,000 models every day. So that is a significant increase to what we were doing in Hadoop with the first product. And this was also the pivot point for us to find that we need to scale out our model building infrastructure. So what Content Queues is it summarizes the tickets of our customers into broad topics. In this case, there's 3 topics, like getting a flight, wanting to cancel a flight, and changing a flight. I mean, it looks at the tickets data for the last 2 months. For any account, they could have up to thousands or 100,000s or even millions of tickets. For any human to read through those tickets and sort it to topics, it's almost inhumane to ask anyone to do that. So, which is why it's helpful for ML to be able to run this through in, say, for 10 to 20 minutes to provide the bird's eye view for customers to see what's happening within their support space. And they can drill into the individual topic, and then it will show like keywords related to that topic, or they can choose to look at the tickets related to the topics as well. They can also provide feedback to us by saying that, all right, I want to dismiss this queue, we call it queue, this topic like suggestion, like queue. You can dismiss the queue saying that it's not good, it's not relevant, or they can choose to resolve a queue, which means that, oh, this is a good suggestion, I've done something, I write an article, I've done something to improve it. And obviously, we have to deal with the issue that we were building 3,000 models with our first product in Hadoop, and it was struggling. It's in our own data center. It's hard for us to scale. The good thing is we are, at that point, moving into AWS, into the cloud. We have more options, more scalable, auto-scaling resources available. And now we need to build these 50,000 models every day. Before I get into how we use AWS Batch to scale up our model building infrastructure, I'll quickly talk about what is the training data, what's the input into Content Queues. So if we are summarizing tickets, obviously we need to pull in tickets data. And because we've moved our infrastructure into AWS means we don't need to use Hadoop to get hold of our tickets data now. Our data lake lives in AWS. So we have our MySQL database that holds our transactional data. We stream them in via change data capture with Kafka, our event bus, into our data lake, which is S3 in AWS. And then that forms our ticket snapshots. And we run Spark jobs to filter and partition those tickets data into individual accounts. And that becomes the training data. So we have one JSON compressed file for each account That becomes the training data for each of the account that uses content queues. And we store it into a bucket. We call it the features bucket. And now that we have all these tickets, we need to group them right into what we see on the screen there. Like you have a title, you have some keywords, and different topics. And the way the grouping works is our data scientists use the research that they've done for the second product answer bot, which is with the embedding space. If we have all these as tickets, and if we run clustering unsupervised classification on them, we can group and cluster them into like clusters. And then based on those ticket tags, we can generate titles. So these clusters will be about canceling flights. And then you can have other clusters about changing flights or adding frequent flyer number. So that becomes what we see on the screen, or well, on the UI. And on a high level, the way the summarization works is that we take in the input ticket, we run it through a deep learning model to embed the text of the ticket into embedding space. And then we would cluster those into different topics. And then for each of the topics, we would generate titles and keywords for that topics. And that becomes the different topics. And that gets written out into a JSON file as our model for each account, a representation of what their ticket topics looks like. At the same time, our data scientists also write out a cluster snapshot file. What that represents is that it allows us to make it faster when we run the clustering again the next time, because the snapshot contains the sketch of each of the clusters. That means when we run it again, we don't have to recluster from sketch all the tickets that we've seen before. We only need to deal with the new tickets that comes in. So in some way, it's some sort of online clustering. Well, I'm happy to take question after, yeah, if you don't mind. Well, the first challenge that we had from the product inception phase was how do we present this on the UI to the user? Well, I've shown you earlier the list view. So that wasn't the first idea that we had during the initial phase. Well, this is simple. This is easy to understand. We explore different options like word clouds or a t-SNE plot like this. So what t-SNE plot does is just it's map your high dimensional data to lower dimensional, which is 2D in this case. And you can imagine all those dots again as tickets. So this is something that our data scientists came up with. But first of all, our UX researcher hated it because she thinks that it's really hard for the customers to understand what's going on looking at those plots. I mean, as fancy and as colorful it may be. And secondly, these t-SNE plots are slow to generate, which means it makes our whole model building process much longer. It will cost more, and it affects our scalability. And what we find is that it's always important to balance the trade-off between your algorithm complexity and the performance of the system that your customer wants. So say, for example, either latency or how fast the model building run or how fast the prediction or inference run. It took me a while to get Pepper to hold on to those toy and quite a few dog treats as well. And the next challenge, of course, is how do we scale out our model building to support the new scale that we needed for content queues. So we realized that there is some similarities between satisfaction prediction and content queues. They both pull in the training data from S3 or some sort of distributed storage. You run it through a scalable compute. Well, for satisfaction, in that case, we use Hadoop, but we could use a different option now. And then they would write out the model file back into a different bucket, a models bucket. And the requirements that we have is we need something that's elastic. So now we need 50,000. We don't know whether the next product will be 100,000 or 130,000, or as the number of customers grow, we might need to support a much larger number of models. We need to support building batches on a recurrent basis for our offline batch model building. We also need to support on-demand building of the models. And of course, we would like to have the flexibility to use CPU or GPU, because obviously using GPU is going to make training your deep learning model much faster. And at that point of time, that was roughly early 2018, I think MLflow wasn't available yet. And the scalable compute options that we look at was, first of all, Elastic MapReduce in AWS. So you could run Spark job or Hadoop job, but it has the same problem as our Hadoop approach, which means you're running batches of the job. It's harder to trigger sort of on-demand any job, any account, just a single account. And there was SageMaker that was newly released at that time. It was an offering by Amazon to sort of train and serve your model. They will handle everything for you. But there was one issue with it that there was there were two limitations with it. They have a service limit on the number of instances that you can have. I think it was 30 at that time. So it means that it's a bottleneck. Like you can only concurrently run up to 30 limit. There's also limits on the number of training jobs that you can run concurrently as well. So it wasn't meeting the use cases that we needed, the requirements of the use cases that we needed. And lastly, there was AWS Batch. For this, it uses job queues to orchestrate your job scheduling, and it provides elastic clusters for you to auto-scale from 0 up to how many vCPU that you needed. So that seems to tick all the boxes that we needed, and hence that was the approach that we went with. The way AWS Batch works is you can define job queues within it, and you can assign priority. Obviously, the higher priority jobs, they will get picked up first, and then the lower priority will get picked up later. And you can define what they call compute environment. Those are basically just your clusters, kind of like your Kubernetes clusters, or in this case, the ECS, the Elastic Container Service clusters in AWS. And you can define the type of instances you want to use in those clusters. So for example, you can define you want to use spot instances, which are the discounted instances offered by AWS, so they are cheaper. And then within that, you can spin up like Docker containers to run your tasks. So we have our model building jobs running as tasks within those clusters. And the way we configure it is we have a spot compute environment and on demand. So because sometimes spot instances, when there's no spare instances, they won't be available. In those cases, you would want to fall back to on demand to make sure that your job doesn't get stuck in the queue. So we always dispatch the job to spot compute environment first, and if there's no available instances, then we fall back to on demand. And overall, the way we run the whole model build through AWS Batch is we use Airflow as our workflow scheduler. It's an open source tool by Airbnb. So that triggers our jobs into the job queues. So you can submit up to 10,000 jobs in a single API calls. So that helps that you don't have to loop through 10,000 times. And once those jobs are queued up in the job queue, they will get triggered or they'll get spawned off as model building jobs within the compute environments. And when those thousands of jobs starts up, they will pull the training data that they need from S3. And once they finish training, those models will get written back to a models bucket in S3. On creation of those models file, AWS would trigger a notification. And those notification events, we listen or we consume them via the notification service into our model building service, our model serving service, sorry. And our serving service would serve up those models to our customers. One thing that we find important here is to pick the right instance type for your jobs. So say, for example, if you pick an instance type that is only 8 gig of memory, and you try to run a job that requires 10 gig of memory, your job will just get stuck in the queue. You can also let Batch decides the instance type for you, but then you kind of lose the flexibility of choosing what instance type you want to use. And the next challenge that we have is, because we're building for so many different accounts, we have big accounts, small accounts, they have different characteristics, or their data has different distribution. So how do we deal with that? So this shows a distribution of the number of tickets across our accounts. Why do I care about number of tickets? Because when we run clustering, the more tickets there is for an account, the longer it will take to cluster, and the more memory it will consume. So as you can see in this case, most of our accounts are on the far left of the graph, which means they have less than 50,000 tickets. As a matter of fact, the median number of tickets our account has was 7,000 plus. But we do have some gigantic account on the far right, like up to 1 million tickets. So if we assign our resources for each job, say, for example, in terms of CPU and memory, just based off those big accounts, that's going to affect, that means we have to give it very high limit. And that is, we know that's not the right way to do. We want to confirm that this is really bad. So we run 50,000 jobs with clusters that can auto-scale up to 2,000 vCPU. This is the CPU utilization graph. You can see that most of the time it's using less than 30% CPU. That means we have a lot of lazy CPU not doing work. We have resource idle, and it took 3.5 days to build those 50,000 models. So that's inefficient. What we did next was to look at the byte size of our training data and bucket our accounts into small, medium, and large. And for the small accounts, we give it less memory and CPU, and the bigger accounts, we just give it more when we dispatch the job. And we rerun the same test again with the same spec, and we find that this time the CPU utilization is much better. It's almost 100% most of the time. And the whole job, the 50,000 job, finished in 7.5 hours, which means we achieved 12 times speed up in terms of building all the models, and also that translates to saving in costs. When we look at our AWS resource usage for this, we were spending roughly about less than $3 for every 1,000 model built, so that was pretty good. So if you use dynamic resource allocation, that's going to optimize both your cost and performance. Now that we have all this scalable infrastructure, V2 of the model building in place, we need to prove its scalability in some ways. And the way we did it is we did a dark launch. That means we turn it on for all accounts 6 months before the product is made generally available. Which means it will exercise the whole pipeline from model building all the way to serving, but we just don't show it on the UI for the customers. And how did that go? Overall, it went well. By using batch with elastic compute and job queue, we had 99.97% of the time it works. It's good. But what happened to the 0.03% of the time when it fails? What happened was we find that the sequence of the ML code itself matters, because the way we are running it, our clustering for content queues is that we have our input ticket, and we take our previous cluster snapshots. That is to restore the cluster shape. And then we build these latest clusters that we have. Once we generated the new clusters, we would upload the clusters into our models bucket in S3. Then we upload this new version of the cluster snapshot file. When we upload the clusters, that is basically, well, if you think of it in terms of like database transaction, that's like a commit in a database transaction. When you have a bunch of statements, that's basically a commit. Because when the new file is available, that will trigger a publish. We said this is a new version of the file. And because we're using spot instances means that AWS can terminate those instances when they need to, because they give you for a cheaper price. So that's the thing you have to deal with. And what it means that when the job is running, say, for example, before we manage to upload the snapshots, if the instance is terminated, then we would have uploaded the clusters, but not the snapshot. What it means is next time when we run the model building job again, it will fail because it says the snapshot is not there. And our fix was literally just to swap the sequence of uploading snapshot and clusters. And what we find is it's really important to keep your model building code within the container to be idempotent. Like when it stops anyway, halfway, retrying it should work. And being in the data conference, memory errors, I'm pretty sure all of us have seen a lot. Like it's the most common thing. So we have some of them as well. And they don't just appear in the largest bucket, the small, medium, large bucket. It could appear in any of the bucket. So an easy fix was to just bump up the memory for those buckets, right? But then at the same time, we know 99.9+%, the other accounts in those buckets, they are fine with the limit. So it's, again, a waste to just bump up all this memory bucket just for this weird 1 or 2 accounts. It could be even their tickets data. They could be writing like a big essay in it that caused this gigantic explosive memory usage. And the way we deal with it is we got a bit more creative. We let it fail. We let the job trigger through batch. And when a job changed from running to failed, batch will emit an event. They call it the job status events. We listen to that event and we consume it with microservices. And then we check, all right, is this job failing because of our memory error? If it is, we'll just give it slightly higher memory limit for this particular job. So that allows us to only bump up the memory for that few kind of weird account. And yeah, it's always something to bear in mind to beware of the outlier memory usage that you might have. Now that we have all this scalable model building running automatically, what happens if we introduce a code in the ML code? Are we going to automatically ship a bunch of content keys that look very weird on the screen to our customers? So that is something that we don't want. And we need to have some sort of validation, automatic validation in place as safeguards. So some of the concerns that we have in this case would be, say for example, if the title of the topic, the grammar looks weird, or if the topic of the title doesn't match all the tickets when the customers drill into it, or if the tickets within the topic, they're about different stuff. And the way our data scientists added this new model validation is by, first of all, getting a human in the loop to label the clusters generated. And from that, they determined that by using the word overlap between the title and the keywords, and the word overlap between the title and the tickets and the keywords provide sufficient sort of safeguard for us to identify bad clusters versus good clusters. So that becomes the last step that we add before a model is deemed published, like the last quality checks, after a model building has finished. And we find that it's very handy to have automatic model validation, especially if you're building a lot of models and it's not feasible to check each of them yourself, like by hand. And in summary, the lessons we learned through this exercise of scaling our model building platform was that it's always important to balance the trade-off between your model complexity and the system performance that you want in terms of latency and so on. You should always pick the right instance type for your job and workload. So using elastic compute with job queues work well for building large batches of models. So if you're not in AWS, perhaps you can use the open source tools like Kubernetes and so on, but you might need to wrap that with other sort of job queue mechanism. By doing dynamic resource allocation, you can save on your cost and performance. And it's important to keep your machine learning code, well, as idempotent as possible within the container. And be prepared to handle outlier memory. And lastly, always have some sort of model validation in place to make sure that you deliver good sort of model to your customers, that you have some sort of safeguard. That's all I have today. Thanks for listening.
You want to take questions?
Yep.
Anybody have questions?
Hey, so I think you answered my question. I was asking why did you have 50,000 models? It looks like you are building one model per customer.
Yes, yes.
Do you have any thoughts on if you guys are solving cold start problem? You're starting up, you have like minimum number of tickets that you have to have before you can get to this stage. Do you have any thoughts on that? Or, I mean, because if, just curious.
No, so the cold start problem was an issue we have with AnswerBot, which is why we went with deep learning approach. But with content queues, because you can't show the topics of account A to account B. You always need to cluster that specific account, so there's no way that you can share it across the different accounts. Yeah.
Other question?
So did you end up using Spark or you end up using AWS Batch?
We use AWS Batch. We just use Spark to generate our training data.
Okay, understand.
Yeah.
Thank you.
Yep. You can use that mic over there too.
So did you guys end up running like one job per account, or was it like one job that triggered for all the accounts?
So we run one job per account. Yeah.
Oh, okay.
And they get dispatched as tasks. And if they failed, for whatever reason, they get retry. You can configure the number of retries as well.
Oh, okay, so that's how you monitor the job failure?
Yeah, and we have monitoring to hook up to any job failures.
Okay. Have you explored running like multiple jobs? Multiple accounts per job, like was that a consideration at all?
We try to, well, especially with this case, we try to keep the data separate. Like we don't want, like multi-tenancy, we don't want don't want the danger of sort of cross-pollinating the data across account, because it's pretty important in terms of data privacy and everything.
Okay, so you didn't want to choose something like a group by account to run on the same job itself, but do the isolation in compute?
Yeah, so because each of the training data is already partitioned by account, So literally, each model building job is just take in this payload from S3 from this path, run the code, the Python code, and write out the model file.
Thanks.
You've spoken a lot about machine learning products that are over here.
Oh, sorry, I was trying.
That are customer-facing at Zendesk. Do you guys have any machine learning products that you use internally? Do you use some of the same infrastructure and techniques as you've talked about here?
No, so we are fairly new, as I said, like we're only 3 years into it, and a lot of the ML product that we built so far is customer-facing, but we are growing our ML team. So when we started, most of our ML team focus are actually situated in Australia, but now we are also expanding to other offices, and we would like to start working on internal-facing ML sort of projects as well.
Hi, thanks for the presentation. Just a quick question. What's on the roadmap for 2019, 2020?
Right, so we're going to expand on AnswerBot, which means we'll start working on this thing we call it concierge, which means when you come in, we try to identify. So AnswerBot just deal with those low-hanging fruit tickets. That means tickets that you can just self-serve with an article. What we're trying to do is go one step forward, which means like, all right, you come to us, what are you trying? Are you trying to look up an order, or are you trying to connect to these other things? So to be a bit smarter, to add more smart to AnswerBot. So that's our next thing.
Hello. In terms of elasticity, load balancing, and failover, could you explain again how did you switch from spot instances to on-demand instances when you were explaining?
Sorry, I didn't quite get the question. You're saying something about load balancing and failover?
Just failover.
Yep.
You were talking about spot instances versus on-demand,
Yep,
right?
yep.
With AWS.
Yep.
So how did you detect
Right.
that, and how did you switch to on-demand?
So how do we deal with the failover when spot instances is not available to go to on-demand? So when you specify compute environment for a job queue in AWS Batch, you can always specify this is the primary compute environment, and you can specify a secondary one. So it's like out of the box. You just said secondary use on-demand, primary use spot. So you always dispatch to spot first. If spot is not available, then it will fall back to on-demand.
Hi, yes. My question's about I don't know if it was all the same model, but at the beginning you were talking about topic modeling.
Yep.
And one thing project we're working on is we would train a model with topic modeling and get specific topics, but then one of the main benefits of topic modeling is it's unsupervised, so it's just generating new topics all the time.
Yes.
How do you manage that kind of or how do you balance that? So you need specific topics because you want to know if the consumer, like if it has to do with canceled reservations, things like that. But then you also want the discovery of new topics that may arise, right? Mm-hmm. So how do you manage that? Was that more of like the specific topics, or did you also have like the discovery of new topics in there?
What do you mean by the specific and the discovery of the new?
Because you had specific topics that were being identified in the topic modeling. So there were canceled flights. I can't remember what the other ones were. But if you constantly retrain the models, then it's going to come up with different topics that are not those, right?
Yeah. So that is where the snapshots becomes handy, because that restore or reinstate your previous run of the topics. That means those topics will still be there. We assign like a cluster ID, which is a unique ID, to each of the topic, so that when we retrain again the next day, those topics will stay, and then the new tickets will get sort of populated back into this embedding space, and if they've gained sufficient size to form a new topics, then those will become the new topics.
Okay, thank you.
Oh, just a second. We're going to run over here. And then you go.
This is kind of related to his question. So you have, in one of the slides, you have the old topic clusters, and then you have the new topic clusters, and the old topic clusters flows into the new topic clusters.
Yep.
So what you just described, you were saying that if the new tickets that come in are of sufficient size to form a new cluster, then you get a new cluster. So
Yep.
would you ever have new tickets that flow into old clusters?
Yes, yes. So you can also continually grow your old clusters. And the way we keep, Well, the way the snapshot works is that you have your topics here with a bunch of tickets, maybe 100 tickets, 200 tickets, or 1,000 tickets. What we do is we pick the 50 most relevant tickets to the centroid of your clusters. So we said these are the tickets that best represent your clusters. So that become the snapshot because that allows you to reform your clusters itself.
Okay.
On
Why
the
not
next run.
just like form new clusters on all tickets? Is it just because it's too intensive?
Yeah, because it will just keep growing, right? If we just keep all the tickets and as we rebuild every day, you add more tickets, eventually it's going to consume too much resources.
Going back to the previous question, so how do you label the new clusters? I mean, is there a human in the loop that inspects these new clusters and says, okay, this is the new topic?
Yep, so we look at the distance because all these are embedding. So we look at the cosine distance and our data scientists apply some sort of formula to it. They kind of patented it. When it's available, I'm pretty sure they will sort of release the details.
Okay, thanks. Any others?
A very basic question. So do you build the new cluster every single day?
Yeah, we refresh those clusters every day.
Okay. Anything else? All right, everybody, please remember to rate the session, and a big thank you to Wai for coming all the way to talk to us today.